Hi, it's Miss Adams from Flamingo Math. We have finally made it to the end of lesson 113, 114, the very last lesson in chapter 1 in AP Pre-Calc. So let's jump right in with example 8. For each of the following scenarios, we want to determine whether a linear, quadratic, or cubic model would be most appropriate, and we have to be able to explain why. For 8A, Al's Food Truck sells Italian panini sandwiches. The price for a panini varies between $4.50 and $8.50, depending on the number of items added to the sandwich. The total number of paninis sold are counted relative to the price of the purchase. To me, that sounds like a linear function. Linear would be the best model. The price depends on the number of items that were added to the panini. Those would have a constant price. So we want to say that in a sentence. So I've said that, something along those lines. Part B, Helen's helium balloons is filling spherical mylar balloons for your 16th birthday party. The radius of each balloon is measured relative to the amount of helium that it contains. Well, we saw earlier that cubic functions have to do with volume, and volume is definitely related to a mylar balloon being filled. So the context is related to volume in a 3D shape that's being filled. And then part C, a buoy is placed in the harbor with a beacon, that light that's mounted at the top to warn boats to know where the harbor begins. The light can be seen from a distance of 1/4 of a mile and rotates in a circular manner every 3 seconds. So that sounds like it's covering area to me. Area is pi r squared. So that sounds reasonable that we could say a quadratic model because the context is related to area. And it's a circular area, pi r squared. Area is pi r squared. So those are pretty straightforward. Let's look at example 9. In example 9, we're given a table that provides data for 5 ordered pairs, and we want to decide which function type best models the data in the table, whether it's linear, quadratic, or cubic. We want to explain our answer using characteristics from the data in the table. So what I did was I went to Desmos, the graphing calculator online, and I entered those values from the table into a regression model. And what I found with the quadratic regression, so here you can see we've got our table from the notes, and we ran a quadratic regression. It doesn't hit the data points very well. So I don't believe it's a quadratic model. Next, I tried the cubic regression. I also did try the linear regression. It was really far off. But the cubic regression, you can see that the table of values, the data that we had, our cubic model fit each one of those data models or data points really well. And I also did the residual plot, which is something that we'll learn about in upcoming lessons from chapter 2. So obviously from the graphing calculator online, it looks like the cubic model is the best model. It fits the data the best. I also did a little bit of calculating and found out that the third differences were roughly -9. The third differences. I'm not going to spend time doing that here in the video. So we could say they are roughly -9. And the regression equation passes through all of the data points. the average rate of change for the third differences were -2. So we could say the average rate of change for the third differences were about -2. And then we want to write the equation of the regression model for the data in the table. I'm going to go back to our image here in Desmos. Let's see, we can delete this. How we can delete that? Delete. Delete. So we've got our reasoning included up here, and we've got the equation here. And for part C, we want to use the model from B to predict the value of y when x is 25. So that's a matter of substituting 25 into our equation here for part B, and it turns out to be about 3.86. We don't know the context of the data, so that's about all we can say in regards to that example. In this next example, we want to construct a rational function model. Knowing if x and y vary directly, then our model can be y equals k of x. K is what's known as the constant of proportionality. And if x is inversely proportional to y, then our data can be modeled by the equation y equals k divided by x. Again, where k is that constant of proportionality. So looking at example 10, the volume of an ideal gas kept at a constant temperature varies inversely with the pressure P that's exerted upon it. So they're telling us it's inverse variation. We know the formula is going to be volume is K divided by P. We want to find the constant of proportionality and write a function to model the volume in terms of the pressure. Well, they told us the volume is 200 cubic centimeters, and it's got to be K divided by 32 kilograms per centimeter squared. So solving for K, we're going to end up with 6,400 kilograms centimeters, because these are going to cancel two of those, and we're cross multiplying 200 times 32 times kilograms times centimeters. So the K value is 6,400 kilogram centimeters. Finding volume then, use the model to find the volume of the gas when the pressure is 40 kilograms per centimeter squared. So setting that up, the volume is 6,400 kilogram centimeters divided by 40 kilogram per centimeter squared. And the kilograms, got a bad letter in there, that's a G. The kilograms are going to cancel each other out. And 6,400 divided by 40 looks like 160. And this comes up here with the other centimeter, so centimeters cubed, which matches the volume is cubic, so we got 160 cubic centimeters. Example 11 is about Hooke's law. Hooke's law tells us that the force required to stretch or compress a spring by some distance is directly proportional to that distance. A force of 275 newtons will stretch a spring 2/10 of a meter. So the formula to me sounds like force is some constant time the distance, since it is direct proportional. And we are given 275 is 0.2 times k. Solving for k, our constant of proportionality is 1375. So we have a formula that we can use, 1375 times a distance. They want us to know how far will a force of 620 newtons, so the force is 620 newtons, and we're looking for the distance. Solving for distance with our calculator is about 0.4509 of a meter, so not even half of a meter. Part B, what force is required to stretch the spring 1/10 of a meter? So force, using the constant that we found, force is 1375D, and we want to stretch it 1/10 of a meter. That's 137.5 newtons is the force required to stretch a meter, to stretch a spring 1/10 of a meter. For example 12, we have the expected population for a herd of buffalo in the Northwest can be modeled by this logistic equation given here, where t is the time in years since 2000. So when t is zero, that's going to represent the year 2000. We want to state the initial population for the herd of buffalo. So enter that into your calculator, and what you want to do to find the initial population would be in that year 2000, so the time is 0. Substituting that in, we've got 112 divided by 1, so there were 112 buffalo initially present in that herd. Next, we want to know what is the rate of change in the number of buffalo from 0 to 25. Include the units and explain the meaning and context. So again, I'm using my calculator to find the P of 25 minus the P of 0. This is the average rate of change in the number of buffalo over that 25-year period. Calculating that with my graphing calculator, I get about 2.4 buffalo per year. So in context, that's the rate of change. Every year, they're adding almost 2.5 buffalo every year. Part C tells us that the function given is valid for 50 years, from 2051 to 2100. Scientists predict that the herd will decline at a constant rate of change of 5 buffalo per year. We want to write a piecewise function, name it B of t, to represent the population of the buffalo in the Northwest for the entire century. So that seems pretty straightforward. They've given us the name of the function, and they told us between the year 2000 and 2050, it's going to follow the model 112 plus 2.75t over 1 plus 0.002t. Now, here's what we've got to find. We've got to figure out the second part that starts at the year 50. We already closed it up here, so it's open here, and goes to the end of the century, so 100 years. But we need to know what happens at 50. So what's the population at 50? If you go back to this equation and plug 50 in here, I get 226.818. You check to make sure that's what you have. And they said that our population is declining at a constant rate of change of 5 buffalo per year. So what kind of equation does that tell us we need to use? My slope is -5. Sounds like a linear equation. Starting at 50, 226.818 minus 5 buffalo per year. So we've written an equation for the first 50 years and then an equation for 2051 to 2100. In our final example, grain is leaking through a hole in a storage bin at a constant rate of 6 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. If the cone is 2 feet tall now, how tall will it be in 1 hour? And notice that volume is given by 1/3 pi r squared h. So what do we know? The height, where did I read it? The height always remains equal to the radius. So first of all, we know height equals radius. And we know the volume is 1/3 pi r squared h. But h is always r. So our volume is pi over 3 r cubed. And we want to know if it's 2 feet tall, and they're giving us everything here is in inches. We want to convert 2 feet tall to 24 inches and substitute right there. That's going to give us volume is pi over 3 times 24 inches to the 3rd power. So volume is 4,608 pi cubic inches. I'm going to leave that right there. So what do we know? We're told that the rate, let's see, it's a constant rate of 6 cubic inches. So they told us the rate is 6 cubic inches per minute, but we've got to turn that into an hour, right? How much would it be in 1 hour? So 6 cubic inches every minute. There are 60 minutes in 1 hour. Minutes cancel. 6 times 60 gives me a rate of 360 cubic inches in an hour. So we want the total volume. Is that what they're asking us to do? That's growth. Okay, the total volume is going to be the 4608 pi plus the 360. So add those up. Volume 1, 4608 plus pi plus 360. Use your calculator to calculate that out. It's 14,836.458 cubic inches. That's our total volume. And then the last thing we got to figure out is the height after an hour. So we got 4608 pi plus 360. And then after an hour, what's the height in 1 hour? So what do we know about the height? The height is going back up here to the equation. We can figure the height is the cube root, if we cross multiply, 3v divided by pi. So I've used this formula to solve for height, and we're going to use that new height formula with our calculator, the height is the cube root of 3 times this volume divided by pi, and I'm getting 24.197 inches. And you can check me with your calculator on that. I also noticed at the end of this set of notes, we provided you with a how to use your TI-84 calculator for scatter plots, and also how to use a TI-Inspire calculator for finding scatter plots and lines of best fit with the instructions in there.